Let's jump into our Blitz review of atomic structure and periodicity. Let's start using phosphorus as our example. So, what makes phosphorus phosphorus? What gives identity to an element is its number of protons, which of course is its atomic number. So phosphorus has 15 protons. Now, to be neutral, we know it will also have 15 electrons. How do we determine neutrons? You take the average atomic mass, round that to a whole number, which then becomes mass number. That is designated as the number of protons and neutrons. And if you subtract from that the atomic number of protons, then you'll get, of course, your number of neutrons. Now, this would be the ratio of your subatomic particles that make up the most common version of phosphorus. But we know that there are at least 2 isotopes of every element, and they differ by the number of neutrons. So, different versions of the same element vary in their number of neutrons or masses, but are identical in the number of protons. This average atomic mass is a weighted average. You take the percentage that we find, or the percent abundance of every isotope. So let's imagine that there are 2 isotopes of phosphorus. So, isotope 1 and isotope 2. And if we know the percent abundances, we can just make up that maybe one version is 30% abundant and the other is 70% abundant. So of 100 atoms, we're likely to encounter this 70 out of the 100. And what we do to get that 30.97, which is on the periodic table, is you take the adjusted percentages, so divide by 100 to undo the percent, multiplied by the specific mass of each isotope, add that, and that's how we get the average atomic mass, which it's an atomic mass unit if it's an individual atom. But of course, we're usually talking about moles practically. So this is grams. In fact, grams of phosphorus in every 1 mole of phosphorus. We want to make sure we're reporting average atomic masses to the 100th place. Okay. This, ladies and gentlemen, just talks about the fundamental structure. All right, so we know phosphorus has those 15 protons and 16 neutrons in the nuclei. And then there's layers of electrons. Now, it is, of course, the attraction of positive protons for the negative electrons that keep them in the nuclei. We can resort to Coulomb's law. Q1, Q2, those will be our charges. Divided by, of course, the distance of those charges. So here, whenever we're talking about the hold of electrons in an atom, we're usually referencing the entire charge or nuclear strength of the nuclei. So for phosphorus, either the Q1 or the Q2, it doesn't matter, would be, our effective nuclear charge, nuclear strength, and that is the number of protons. And then Q2, if we're talking about an individual electron, well, that would just be -1. And then this would be the distance from, the center of the nuclei, really, to wherever that electron is. So let's talk about the electron configuration of phosphorus. So we know, now that is a ridiculous over-exaggeration of the size of the nucleus, we know that. But we know that there are layers of electrons, energy levels, and that energy levels are made of sublevels. Sublevels are made of orbitals. If we recall back, we can structure the periodic table. Remember this, we can break it into the S, P, D, and F block, and just use the position on the periodic table to help us to get electron configuration. We don't have to memorize that off-ball chart. So, for phosphorus, with those 15 electrons, the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p3. All right, to get to phosphorus, we would first go through the 1s. Remember, helium really should be here. And then the 2s, the 2p. So remember, the period number is the energy level of the s and the p. So 1s, 2s, 2p, 3s, and then 1, 2, 3, the third position of the 3p. This would be the electron configuration of phosphorus. So, it would depend if we're trying to talk about how strongly is the first energy level, which would be the 1s. Now we know that will be held the most strongly. So there's 15 protons for that one electron in that first energy level. And the distance, it's only the first energy level. So the smaller our denominator, we know the larger. This would be, we could say force of attraction, strength that's holding the electron within the atom. Okay, what if you were asked to give the electron configuration of phosphide? Well, we know that the octet rule will drive us, and originally phosphorus has 5 valence, but it will pick up another 3 to get the octet rule satisfied, which just our world tells us gives us stability of ions, or lower energy, of course. Okay, what about shorthand configuration? Well, most times the College Board asks for complete electron configuration. You can always do shorthand, always, if you're doing a free response, especially if you're backing up a justification. But if they ask for an electron configuration, they'll usually ask for a complete configuration. Otherwise, for phosphorus, you refer to the noble gas before it, which would be neon, and then you begin to add on. So 3s2, 3p3. Now for phosphide, still refer to the noble gas before it, which would be neon, and then 3s2, 3p6. Now remember, orbital notation, that's with the arrows. Now usually orbital notation comes our way more with multiple choice questions. But remember, just to show these valence, so the 3s, remember electrons when paired have opposite spins. Hund's rule says when electrons are filling degenerate, so these are equal energy orbitals, they will reside solo with the same spin, then partner up. Now, we can observe that electrons do travel in pairs with opposite spin, and our understanding is they must rotate oppositely to lower energy. However, whenever they're paired, there's still going to be electron-electron repulsion. So remember, talking about the trends of size, we'll get to that, but to make a pair, you're still causing electrons to repel each other. All right, let's talk about the electron configuration of iron. So for iron, 26 protons, so neutral will be 26 electrons. So iron would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, iron is located in the D block, and the first time we have D sublevels is in the third energy level, which we begin to fill after the 4s. So the D block, the energy level is 1 minus the row number. So we have 4s, 3d, then 4p. 5s, then 4d, then 5p. And iron is 1, 2, 3, 4, 5, 6 positions over. Now, remember there are some exceptions to electron configuration. We are not expected for the AP Chem exam to know those, but if something would be given to us, we'd have to justify it. And you want to look at the configuration, and if it's an out of ordinary configuration, it's that configuration must be delivering a lower energy overall for the atom or ion. All right, iron, we know forms a cation because it is a metal. Not expected to know this, but iron often is found as a +2 or a +3. What would the electron configuration of +2 be? If you want to think about this for a moment. Now, it's easier for us to come up with the electron configuration of anions. But with cations, we have to be careful. The same thing applies with cations as with anions. Just like you add to valence, you take from valence. So for iron to form a +2, my valence electrons, those belong to the highest energy level. They're going to come from this 4s. So iron +2 would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Now, iron +3, then we'll start taking from the 3d. That would be 1s2, but then 3p6, 3d5. So be very careful. The College Board has asked for these most recently. Okay, so we've gone over a little bit of electron configuration. Now, while we were learning this in Chapter 7, we did not talk about PES spectrums or graphs. PES is photoelectron spectroscopy. All right, so what we do is we take an atom, so let's say phosphorus, and we bombard it with ultraviolet radiation. And we keep increasing the energy or decreasing frequencies, or increasing frequency, decreasing wavelength, until we eject electrons. And we measure the energy at which they're ejected and then the relative abundance or the number of electrons. And then we graph it. So most often, PES comes your way in a graph. And it'll be energy, and usually they're crazy units like megajoule per mole and stuff like that, per mole of electrons. And then on your y-axis is the relative number of electrons. Okay, so where the peak is on the x-axis is how much energy was required to eject those electrons. And what will determine the energy is where is the electron in reference to the nucleus. Coulomb's law. All right, now, often PES spectrums are from higher energy to low, and that's odd for us because usually an x-axis goes from 0 and up, or a low value to a high value. So we just have to be on guard for that. The height of the peak is the number of electrons. Okay, what I would always do first when given a PES spectrum is find where my 1s electrons are. They are going to require the greatest amount of energy to eject. The ones closest to the nucleus are going to be held the strongest because they're the shortest distance. So if you're high to low, it's going to be the peak. And most often we're given ground state configuration. So all the electrons are there in the lowest energy. They're not excited. So whatever your first peak is, if it's going from high to low, that's going to be your 1s. And unless it's, hydrogen, you're going to have 2 electrons there. Usually, you are given a scale, very, very nice, but we can just conclude based upon the height, again, unless it's hydrogen and you only have 1 electron, the 1s will have 2 electrons. So that can be used as a reference to judge the other peaks. Now, for phosphorus, which we know is this configuration, we're going to have 1, 2, 3, 4, 5 peaks. Now, the 2s is of lower energy as far as the electrons are concerned, but they're held the most strongly. Okay, so they're going to be close to the energy of the 2p because they're both in the second energy level, but they still differ in energy. So we would expect for phosphorus that, somewhere the next we would have is a 2, and then 1 that's going to be much higher, that'll be the 2p. Oh, I made it look too high. And then we'll have our 3s, and then the 3p would be just 3. So, this is something that very easy to answer questions about. Now, what kind of questions might come our way? Well, we could be asked, for example, if given this spectrum, we could be asked to identify the element. Now, megajoules per mole, and I see 1,000 to 0.1. So I know my 1s is going to be the peak furthest to the left. And look, yep, it's filled. Then 2s. Then 2p. Okay, and what element is that? That is going to be carbon. So we could be given this and asked to identify the element. We also could be asked to circle a specific sublevel. So it may say, on the above PES spectrum of carbon, circle the peak that represents the 2s electrons, which we would just circle that. We could be asked to identify the peak of the electrons that are closest to the nucleus, which would be this. We could be asked, where will the electrons be removed first when energy is inputted? Which we know we're going to remove from outside in. So this would be the peak that would represent the electrons that would be removed first, which would be from the 2p. And remember, the energy that would be required to eject those electrons, that's ionization energy, which we'll come back to in just a moment. So those are usually the kinds of questions. The only other thing is they could possibly ask for you, if given a PES spectrum, to draw where, let's say, the 2s peak for, let's just say, silicon would be. Okay, well, silicon, okay, the 2s peak of silicon still has 2 electrons. It's going to be just as high. But what would be different about the electrons in carbon's 2s versus silicon's 2s? They're both in the second energy level. But what is holding those electrons is a different number of protons for carbon versus silicon. Silicon has 14, where carbon just has 6. So we would infer definitely that these would be held more strongly. They're going to be closer to the nucleus. So the 2s that I would draw for carbon, still the same height, but it would be to the, for silicon, it would be to the left of the 2s for carbon. Okay, so those are usually, the things that come our way. All right, so that's a review of atomic structure, some electron config, and PES spectrum. But what about periodic trends? All right, so we know the periodic table is periodic because as one proceeds down groups or families, and then from left to right across a period, or right to left, or down up, we know that the chemical and physical properties repeat themselves in a regular repeating pattern. All right, the two most often asked about trends are atomic size or atomic radius. And of course, radius, because it's really hard to measure exactly where the edge is of an atom. So if we bond, let's say, a hydrogen to another hydrogen, we can pinpoint where the nuclei are and divide that in half. So we're really kind of measuring the diameter, but that's usually why we just report it as atomic radius, but one and the same. Atomic size and ionization energy. Those are the two favorites to be asked specifically for you to explain and justify. However, we know that we also have electron affinity and electronegativity. This plays more, of course, with intermolecular forces and polarity of molecules and polarity of bonds and that kind of thing. So for our Blitz review, we'll just talk about these two periodic trends. Okay, atomic size. So we know as we proceed down the periodic table, our atoms get larger. However, from left to right, our atoms get smaller. And why is that? All right. So as we go from top to bottom, we get larger. And as we go from left to right, we get smaller. Okay, but of course, why is that? All right, if you are asked to justify something about size and you're comparing things in the same group or family, but they are in different periods, well, the difference is, of course, the different energy levels. So if we want to rely, upon Coulomb's law, we are greatly varying the distance. So if we talk about sodium, which has its outermost electrons in the 3s versus cesium, which has its outermost electrons in the 6s, this is much larger because of the greater distance of the electrons from the nuclei. Okay, so we want to talk about number of electron levels or energy levels. You could call them shells, etc. Okay, but what about across a period? Across a period, so if we want to do the third period, and let's go ahead with sodium, 3s, and sulfur, 3p. Okay, well then we need to talk about effective nuclear charge, because in essence, these are the same quote-unquote distance, because it's the third energy level. So what is the strength of the nucleus that's holding those electrons, which are approximately the same distance? So sodium, of course, 11 protons, sulfur, of course, 16 protons. So the greater effective nuclear charge of sodium, greater than sulfur. So the greater effective nuclear charge of sulfur, greater than sodium. So it has a stronger pull on the electrons in the third energy level compared to sodium. And again, backing it up with Coulomb's law. Ionization energy, the energy that must be invested in an element. So, for example, chlorine, the amount of energy, and usually it's a gaseous atom, but that's okay for us to not remember specifically, but the amount of energy that must be invested to remove an electron. Removing an electron, we're making a cation. I know it was weird for halogens. And the amount of energy will depend on where are we removing that electron. In some example free response questions, we'll look at comparing different elements and backing up with Coulomb's law. Please take a look at the example free response questions that I have solved for us on atomic structure and periodicity. Remember with this, we want to really rely on our knowledge of the periodic table. We want to really understand and apply our understanding of strength of nucleus and electron structure. All right, good luck, students.